Welcome back to the course on computer network and internet protocols. So, in the last class we have discussed about the transmission control protocol or the TCP and the several features which are there in TCP. So, in this class we will discuss about another transport layer protocol which is not that much widely used as TCP, but still many of the applications uses that. We call it as user datagram protocol or UDP. Apart from UDP, we will discuss another protocol which is recently developed by Google and gradually getting popularity over the internet, which we call as the QUIC, and that QUIC it uses this UDP as the underlying transport layer protocol. So, the basic difference between the TCP and UDP is that UDP actually is a very simple protocol and it does not support the functionalities which are provided by TCP. So, as we have seen that the TCP protocol, it supports the connection establishment, reliable data delivery, flow control, congestion control, ordered packet delivery, all these different features. But to implement this kind of features in TCP, certainly the protocol has a significant amount of overhead or the signaling overhead, what we call it in the networking term. So, this signaling overhead is something like this: to make the protocol correct or to make the operation of the protocol correct, you are sending some additional data to the internet. So, for example, for the connection establishment and the connection release, you need to send or you need to have this three-way handshaking mechanism, which is time consuming. So, for every individual data packet, if you think about multiple short flows which are flowing in the network, just like whenever you are doing web browsing, during that time, if you are sending such multiple short flows, that means HTTP request response messages, and if every request response message is embedded in a TCP connection, then that is a problematic, because for this request response message you require 3 messages for connection establishment and 3 messages for connection closure. So, that is one of the overhead. The second overhead which comes from the flow control and the congestion control algorithm. So, if the protocol detects that there is a packet loss, you need to retransmit it, and retransmit always block the flow of the existing data packet or the new data packets. On the other hand, if you look into the congestion control algorithm, the congestion control algorithm, to make the congestion control algorithm distributed and to support maximum fairness, we make the protocol in such a way that you have to start from the slow start phase. That means, you need to start from a very low value of the congestion window and gradually increase that value to reach the capacity, because you do not know the capacity. Now, if you think about a high speed link, in that high speed link itself, you are starting from a very low value of the congestion window and then applying the slow start to reach at the operating point. But with this, if you just think about your flows are very short, just like a HTTP request response message, by the time the TCP flow will reach to the operating point, the connection will get closed, because you have transferred your request and response message for HTTP, and you will again start a new TCP with this new set of congestion control algorithm or the new set of slow start mechanism. So, because of this, this protocol, the TCP, it has this significant amount of overhead, which makes the protocol very slow for practical deployment. Although it supports a good amount of reliability and works perfectly or works correctly over a real network. But for many of the application, we do not tolerate, or we are not able to tolerate, or sometimes we do not require this kind of additional services. What is more required is to send the data somehow at the other end and then just parse the data. So, one application is just like your DNS protocol or the domain name system protocol. So, the DNS protocol for sending a DNS request and a DNS response, you do not require a TCP connection establishment, because that is going to be a significant overhead. Rather, you just send the DNS simply the DNS message, and if the DNS message is not response, you will certainly have a timeout at the sender side. You can again request for the domain name with the next message. So, for that we support this user datagram protocol or UDP protocol in the internet. So, this UDP just provide you the end-to-end packet delivery, or in UDP we term it as the datagram. So, end-to-end in datagram delivery. So, it does not provide any of the services like this connection establishment, reliable data delivery, flow control and congestion control, ordered packet delivery, all these things in the network. So, these are the broad features and the uses of TCP. So, the feature is that first of all it is a very simple protocol, it is or sometimes we say that it is not at all a transport layer protocol, it is just like a wrapper on top of the IP layer. So, whatever services is being provided by the IP layer, the same set of service is just forwarded to the application by bypassing the basic transport layer functionality. So, UDP works like a wrapper on top of the IP layer. The protocol is very fast, because you do not need to wait for this slow start phase, you do not need to wait for the connection establishment and the connection closure, and you do not have any flow control and the congestion control algorithm. The protocol itself is very fast and it works nicely when the network has a low loss probability. So, the use cases of UDP is to provide performance. You do not have any buffer like TCP. So, you can give or support a protocol with faster delivery whenever your link is good, or you do not bother about a packet loss, and it is a kind of short and sweet protocol. So, it does not have any overhead and it is suitable for short message transfer just like the domain name system. So, as I have mentioned that UDP is connectionless and unreliable. So, you just send data packets or datagrams one after another. If a datagram is being lost, the server does not take care of that, the packet get lost. So, you do not care about that. So, if the application cares about packet loss, the application will apply its own acknowledgement mechanism or its own procedure for handling or recovering from the loss. So, you just create a datagram and send it one after another. So, you do not have any connection establishment, you do not bother about whether the server is running or not, you simply send a packet, you do not have any reliability and no acknowledgement mechanism. So, this is the structure of the UDP header. So, earlier we have looked into the structure of the TCP header. So, compared to the TCP header, this UDP header is fairly simple. You only have 4 different fields: the source port, the destination port, the length and the checksum. That is all, and then you have the data. So, the source port and the destination port are the server port and the client port. The length of the packet which is required to find out that how much data is there in your UDP datagram, and the checksum field to check the correctness of the packet. So, although reliability is not implemented, but at the server side or the destination side, you want to find out whether the packet or the datagram that you have received, whether that is a correct datagram or something got some mishap has happened or something got flipped. So, you want to find out that. So, that is why we put the checksum field. Now, this checksum calculation in TCP and UDP. So, I have not mentioned that during the discussion of TCP, just kept it for the discussion here. So, this checksum calculation in TCP and UDP is a nice feature. So, how checksum is calculated or what is checksum? The details of checksum we will discuss later on, while we will look into various error correction codes in the context of data link layer. But just to give you a brief idea that checksum is nothing but a function. So, you can think of checksum as a function if. So, inside that function you are providing the message and then you are getting certain value. So, whatever value you are getting, so this C, this is the checksum. So, that C you are putting here. Now, because checksum is of fixed length, you can think of this function as a hash function. So, any hash function can be used as a checksum, but ideally this IP checksum or internet checksum which we apply for network data transfer, it is not a complicated hash function like our traditional cryptographic hash function, because we do not require that one way property that much. Rather, we are just concerned about to get a fixed size message digest out of the message. So, that is why this internet checksum computation is fairly simple, and if you again apply a cryptographic hash or a complicated hash function here, it will take a significant amount of time to compute that corresponding checksum. So, that we do not want. So, we simply use a simple method for doing the checksum. So, the simple method, as the name suggests in internet, checksum is just like you divide the entire message into fixed size block and then make a one's complement addition to compute the checksum. So, that is the basic idea of internet checksum that we apply here. Now, in internet checksum, so the detailed procedure of internet checksum and example we will discuss later while we discuss about the error correcting code, as I mentioned just before. But ultimately this checksum is giving you a fixed size code, that is the C. Now, whenever you are receiving this message at the receiver end, what you do, whatever you are receiving with this received data, again you apply the same function to compute the checksum and find out that what is the checksum that has been transferred with the message and the checksum that has been computed at the receiver side, whether they are getting matched or not. If they are getting matched, that means whatever value has been transferred from the sender side, you have received that particular value. Now, again remember that checksum is not to ensure packet integrity from the security attacks or the external attacks. It is just to ensure packet integrity from the network fault or the system faults. So, whenever you are transferring the data, because many of the time you are doing a digital to analog conversion or analog to digital conversion, then encoding decoding of packet, you are applying the modulation technique at the physical layer. So, it may happen because of this sampling error or the quantization error, some bit ideally or it was 1, but that got flipped to 0 during this analog digital conversion or the modulation and coding steps, or some 0 bits got flipped to 1. So, just to detect those kind of things, we apply the checksum. It is not to ensure that the packet is free or the packet has saved from some security attack based on the cryptography or network security point of view. So, because of that, so whatever checksum you are getting at the receiver side, you compute the checksum value that has been transferred with the packet. If they matches, that means the packet integrity got preserved, there was no such error that has been introduced during signal processing, and you have received the correct datagram that was sent by the sender. Now, while compute the checksum in TCP and UDP, TCP and UDP take certain things into consideration during checksum computation. So, as we have said that checksum is nothing but a function m, where you are taking a message m as input and you are computing the checksum value. Now, in this message, so TCP or UDP, they put TCP or UDP header plus the data that you are sending plus a pseudo header. So, this pseudo header is actually not transmitted with the packet, it is just used for the computation of checksum, and once the checksum is computed, that pseudo header is getting dropped, or that gets dropped. So, what is the content of this pseudo header? The content of the pseudo header is the source IP, the destination IP, then the protocol field from the IP header. So, it actually takes certain fields from the IP header. So, all these frame fields are coming from the IP header, and the fourth is the reserved bits. So, there are 8 reserved bits in IP. So, those reserved bits from the IP header. So, all these fields comes from the IP header. So, that way we consider this pseudo header in the computation of checksum, but remember that this pseudo header is not transmitted with the packet, rather once you have computed the checksum, then you just put the checksum and discard the pseudo header. At the receiver end, receiver will again construct the pseudo header and compute the checksum, make a match with the received checksum and drop that pseudo header. Now, the thing is that what is the purpose of including this pseudo header in the checksum computation? So, this pseudo header is included in the checksum computation just to do a double validation of the source IP, destination IP and the protocol field and the result value field. So, these fields are very important from the perspective of transmission of a packet, because these fields actually help you to identify the correct source and the correct destination. So, although IP header includes its own checksum field, but this IP header changes the checksum at every individual layer, because if you look into the network diagram, you have this source followed by multiple hops routers, and then finally is your destination. Now, every router, they apply the routing mechanism, they look into the IP header, they may make they may change the IP header, and then they again compute the checksum, the IP header checksum, and put it at the part of the IP header. So, that is why the checksum which is there in the IP header, they may get changed whenever you are going from one layer 3 hop to another layer 3 hop. So, all these are the layer 3 devices. So, whenever you are going from one layer 3 hop to another layer 3 hop, then the things may get changed. But at the same time, we do a end-to-end validation with this end-to-end protocol. So, these transport layer protocols are basically the end-to-end protocol. So, the UDP header or the TCP header never gets changed at the lower layer of the protocol stack, at the internet layer of the protocol stack. So, the UDP header or the TCP header will never get changed at the individual routers. So, that is why we make a double check in the TCP header or the UDP header by putting this pseudo header at the source IP, destination IP, all these fields, that this intermediate router somehow there these fields has not got changed. Because in the router, if you later on will discuss the entire processing of the routers, you will see that whenever it receives an IP packet, it takes the IP header out, applies the routing mechanism, then again adapt the IP header and send it to the outgoing link. Because that IP layer processing is done at the router level. So, if there is certain inconsistency or certain faults inside the router, that may introduce an error to the source IP or the destination IP field. So, we want to make sure through this integrity change at the UDP header that no such error has been occurred during the transmission of the transport layer segment or in TCP or the transport layer datagram at UDP. So, that is why we put the pseudo header as a part of the checksum computation. But as I have mentioned earlier, again repeatedly I am mentioning that this pseudo header is just used only for the computation of the checksum, and this pseudo header is not transmitted during the transfer of the data. That is just to check this end-to-end integrity of the data transmission. Okay. Now, there are multiple applications that uses UDP, as we have looked earlier, the DNS protocol, the domain name system protocol. It is a simple request response message. So, we require it faster than TCP. So, we apply UDP there. Then this BootP or DHCP, they are the network configuration protocol. Again, they are short messaging protocol, which helps faster configuration of the devices. TFTP, trivial file transfer protocol, it is a simple lightweight file transfer protocol to transfer small files. SNMP, the network management protocol or the simple network management protocol, it is again a simple UDP protocol, which is easily cut through congestion than TCP. So, in TCP, if there is a congestion, then TCP reduce the rate. But in case of UDP, as it does not take care of the congestion, if the packet comes to the buffer and if it is not dropped from that intermediate buffer, eventually it will get transmitted. So, that is why we use this UDP in case of SNMP. Then the interesting protocol comes, which is Quick UDP internet connection, that was developed by Google a couple of years back, which is the advance of the transport protocol. So, idea behind Quick is to overcome many of the shortcomings which were there in TCP, because of this slow start phase, the connection establishment for every individual flow. In Quick, UDP provide a direct access to IP. So, with the help of UDP, what Quick does that it directly send the packet via IP, but whatever additional facilities like flow control, congestion control, reliability, all these things are there, they are implemented as a part of application with a secure binding. So, let us look briefly about how Quick works. The full form of Quick is Quick UDP Internet Connection. The first paper of Quick or the detailed paper of research paper of Quick that came from Google in 2017 SIGCOMM. So, I suggest all of you to go through that paper to know more details about Quick. Also, you can see the internet draft of Quick to look into the specific protocol. So, if you look into the difference between the application over TCP and the application over Quick. So, in bottom we have the IP layer. Whenever you are applying HTTP or say HTTPS, the secure version of the HTTP. So, under HTTP you apply a encryption layer through transport layer security or secure socket layer, and then you use TCP to transfer the data at IP. Now, what Quick does, it makes a direct interaction with HTTP. So, HTTP runs on top of this Quick and Quick runs on top of the UDP and it then access IP. Now, this security features, the encryption part, it is embedded inside the Quick protocol. So, you do not require any other secure layer. So, every Quick packet is end to end encrypted and it provides end to end security. So, you do not require another security layer that we require in case of TCP with the help of SSL or secure socket layer or transport layer security protocol. So, this SSL and TLS, this kind of encryption protocols are not required in case of Quick, because Quick inherently applies the security features. Okay. So, one of the important aspect of Quick is to combine multiple short flows together. So, if you remember the problem which is there in TCP, the problem that I was explaining earlier, that if you want to transfer one HTTP packet in HTTP 1.1, you had one TCP connection for every request response message, and even with HTTP 1.2, HTTP 1.1, what you had that you can combine multiple request response together, but based on the web browsing nature, normally we browse a web, then we wait for a certain time and then we move to another page, and during that time, although it is combining multiple such request response together, but that mostly related or mostly limited to a single session. Whenever you are moving to a different page, you need to create a different TCP connection. Now, for every TCP connection, you require three-way handshaking. So, just to send a few HTTP request response message, you require three connection at three-way handshaking at the sender side and a three-way handshaking during the connection termination as well. Now, Quick actually solves this problem in this way. So, in case of Quick, during the initial handshaking, whenever you are connecting to the server for the first time, during that time you have to do a detailed handshaking, but after that you do not need to do that detailed handshaking, rather you can directly use the previous handshaking part, the connection that has already been established, to send further data. So, this works in this way. So, as I have mentioned that Quick is an end to end encryption protocol, because of that you require certain credential from the server. Now, initially the client does not have those kind of credentials. So, the client sends a equate hello, client hello. When the client says this equate client hello, which is received by the server, and the server finds it out that the client hello does not has the required security certificate, it sends a reject message, and with this reject message the server sends the security credential to the client. Now, the client has this security credential. With this security credential, it sends a complete client hello. Now, here the interesting thing is that because the client has already received this reject message from the server, the client actually knows that the server is running and the server is ready to accept packet. So, the client can start sending encrypted request. Now, if the server wants to send the message from the server side to the client side, that means the responses, the server sends a server hello initially. After this server hello is sent, because the server has already received the client credential from this client hello, it starts sending the encrypted responses from the server side. So, you actually required one RTT here. Now, once this connection has been established, then for the next ongoing connections between the same set of client server, you do not require this one RTT handshake, rather you require a 0 RTT handshake. That means, you already have received the server credential. Because you already have received the server credential, you can start with this complete client hello, and you know that the server is running because it has already received certain packets. So, you can start sending the encrypted request, and if the server wants to send data to the client, server start with a server hello and then the encrypted responses. This is not only one encrypted responses, it can send multiple responses or here multiple requests simultaneously. Now, sometime it may happen that during this time it may happen that the server credential has been changed. If the server credential has been changed, when the server received this complete client hello, the server sends a reject message with the updated server credential. Now, with this updated server credential, the client can reinitiate the connection and start sending the request. So, whenever the server credential gets changed, you require a 1 RTT handshake, and at the initial time you require a 1 RTT handshake. After in between, you can always use the 0 RTT handshake to transfer the packets. Okay. Another interesting feature of Quick is to support multi-streaming, and it supports something called Headofline Blocking free protocol. I will come to that point of what is meant by Headofline blocking in a couple of minutes. So, what happens in HTTP 1.1 that you can have multiple TCP streams one after another, and with these multiple TCP streams you can send multiple, with every TCP stream you can send multiple request response messages in between the client and the server. But because you are having these multiple TCP streams in parallel, for every individual stream you should have this connection establishment, and every TCP stream will go through the slow start phase. So, that is the overhead for HTTP 1.1. So, that is why in HTTP 2 or sometime that was earlier proposal from Google, they call that particular protocol as SPDY. So, in that particular protocol you can multiplex multiple streams together. So, here you are combining all these streams together and have a single TCP connection between the server and the client. So, here all these streams are getting multiplexed to a single stream, and this multiple stream is sent to the client. So, in this case we have a problem called Headofline blocking. What is that? Say the nature of the TCP is that if it receives a single out of order packet, then it put that out of order packet in the buffer and start sending duplicate acknowledgements. But if it does not receive in order packet, then it will not send the packet to the application. Now, here whenever you are combining multiple streams together, what happens, even if a single packet get lost, because of that single packet lost, this entire TCP connection will get blocked, and which will in turn block all the streams, even if certain packets from certain streams are receiving at the buffer. So, because you have a single connection, say assume a red packet got lost, and this is the stream corresponds to the red packet, these are the streams corresponds to the blue packets and the black packets. Even if you are receiving blue packets and the black packets, because you have a single TCP connection, the TCP connection will not send those packets to the corresponding stream. So, those streams will also get blocked. So, this is called the Headofline blocking. Now, Quick solves this Headofline blocking problem by using UDP connection. So, UDP connection does not have this problem of blocking due to reordering. So, UDP simply passes the packet to the streams, and then the streams take care of the Quick protocol itself takes care of the sending the packet to the individual streams, and it maintains the stream wise flow control and the congestion control algorithm. So, I am not going to the flow control and the congestion control algorithm of Quick in detail. If you are interested, you can look into the specific draft or the SIGCOMM 2017 paper. Another interesting feature in QUIC is that TCP uses this duplicate acknowledgement, but QUIC does not use the duplicate acknowledgement. Even for a retransmission, it assigns a new sequence number to the packet. So, because the packets are basically transmitted over UDP, QUIC is not a stream oriented protocol, it does not use the byte sequence number, rather it uses the packet sequence number for simplicity, and for every packet, that means the original packet as well as the retransmitted packet, it puts a new sequence number. So, that is why you do not have this problem of duplicate sequence number and blocking due to these duplicate acknowledgements. So, these are few of the features of QUIC, and this protocol QUIC is gradually getting popularity in the internet. Many of the services like YouTube or Google Drive, which is coming from Google, Google has already started a deployment of QUIC, and the current version of Chromium based browsers, they have the implementation of QUIC. So, many of the recent protocols have started using QUIC. Recent applications, or mostly all the applications from Google, they have started using QUIC. Possibly QUIC is the future protocol which is going to replace the standard TCP based data delivery, and during that time UDP is actually going to be more important compared to TCP. So, that is possibly the future of internet. So, that is all about the transport layer protocol, different kind of transport layer protocol. In the next couple of classes, we will do a practical thing. We will look into this concept of socket programming and network programming. We will see that with the help of the socket programming, how you can access a specific transport layer protocol and you can start transmission of data, and you can write your own application by utilizing this different type of transport layer protocol. We will see certain demo of that, and then we will move to the next layer of the protocol stack, that is the internet layer or the network layer of the protocol stack. Thank you all for attending this class. See you again.